There's a glass of water sitting on my counter right now, and by every modern standard, it shouldn't be safe to drink. No filter, no electricity, no UV light, no chemical tablets, no system you can plug in, replace, or subscribe to. Just water and two small pieces of metal resting quietly at the bottom. If you walked into this room, you'd probably assume that water is untreated, maybe even dangerous, because that's what we've been taught, that clean water requires a device, a process, a system controlled from the outside. But what if the system was never external to begin with? What if purification could happen passively, silently, without any moving parts? This isn't a survival trick, it's not a hack. It's something far more interesting, a biological system that has been observed, documented, and quietly understood for thousands of years. Ancient civilizations used it without knowing the chemistry. Modern science has confirmed it again and again. And yet, it almost never appears in the systems we rely on today. Not because it doesn't work, but because it doesn't fit the way modern systems are designed. And once you see how it works, you'll start to question what else has been left out. Before we talk about metals, reactions, or ancient methods, we need to understand something more fundamental, what it actually means to make water safe. Because most people assume that clean water is about removing what you can see, particles, dirt, cloudiness. But the real danger in water isn't what you see, it's what's alive inside it. Bacteria are not passive contaminants, they are living systems. They feed, reproduce, and adapt to their environment. Give them moisture, the right temperature, and a stable surface, and they multiply exponentially. This is where most modern thinking creates a blind spot. We've been trained to think in terms of filtration, pushing water through a barrier to trap physical material. And while that's important, filtration alone doesn't necessarily stop biological activity. It changes the environment, but it doesn't always eliminate the organisms themselves. So when you step back and look at water treatment as a system, you begin to see two distinct layers. The first is physical, removing particles and debris. The second is biological, stopping life at the cellular level. Ancient systems focused heavily on that second layer, not just filtering water, but actively disrupting the conditions that allow microorganisms to survive. And once you understand that distinction, everything else starts to make sense. Now we can finally look at the mechanism behind that glass of water, and why something as simple as metal can change its biological reality. There is a phenomenon, formally identified in the late 19th century, known as the oligodynamic effect. It describes how certain metals, even in extremely small amounts, release ions that are toxic to microorganisms. But toxic doesn't quite capture what's really happening. When copper ions enter the water, they don't target a single function inside the bacteria. They don't block one pathway or interrupt one process. Instead, they attack the cell on multiple levels at the same time. They destabilize the cell membrane, causing it to lose structural integrity. They interfere with proteins, preventing essential biological reactions. They damage genetic material, disrupting replication. And they impair the cell's ability to produce energy. This is not a precision strike. It's a full system collapse. And that difference matters, because when a treatment targets only one pathway, bacteria can adapt. They mutate. They develop resistance. That's the entire problem behind antibiotic-resistant strains. But when the attack is structural, when it affects everything at once, there is no single adaptation that can protect the organism. The system doesn't weaken the bacteria. It removes its ability to exist. Copper on its own is already powerful. It can disrupt bacterial systems, reduce populations, and given enough time, eliminate many common pathogens. But when you introduce a second metal into that same environment, the system changes, because now you're no longer dealing with a static material. You're creating interaction. When copper and zinc sit in water and come into contact with each other, they form what's known as a galvanic cell, essentially a tiny self-generated battery. Electrons begin to flow from one metal to the other through the surrounding water, and that flow does something critical. It accelerates the release of metal ions into the water. Instead of a slow, passive process, you now have a dynamic system where ion exchange is happening more rapidly and more consistently over time. But the effect isn't just faster, it's broader. Copper and zinc don't attack bacteria in exactly the same way. They interfere with different cellular functions, different enzymes, different structural components. So when both are present, the coverage expands. More pathways are disrupted, more systems are affected. What you end up with isn't just a stronger version of the same idea. It's a layered biological system, self-powered, continuous, and far more efficient than either metal alone. Once you understand the system, the actual build becomes surprisingly simple. This isn't a complex device. There are no moving parts, no calibration, no electronics, just materials, surface area, and time. You start with two components, a piece of copper and a piece of zinc. These don't need to be specialized or expensive. A short section of copper pipe, some copper wire, or even a small mesh will work. For zinc, a galvanized bolt or fitting is enough. Before placing them in water, clean both surfaces thoroughly. A simple rinse with white vinegar removes oxidation and any residue that might block ion exchange. What matters is direct contact between clean metal and water. Next, place both metals at the bottom of a container. Glass, ceramic, or stainless steel are ideal. Avoid plastic for long-term storage, as it can introduce unwanted compounds into the water. Make sure the two metals are touching or very close to each other. That contact allows the galvanic interaction to occur. Then fill the container and let the system sit undisturbed for at least 6 to 8 hours. One key principle here is surface area. The more exposed metal in contact with water, the more active the system becomes. No power, no input, just a passive system, doing its work over time. At this point, it's easy to see this system as a complete solution. But it's not, and understanding where it fails is just as important as understanding how it works, because this system operates on a biological level, not a physical or chemical one. It disrupts microorganisms. It reduces bacterial load. It can significantly improve the safety of water over time, but it does not remove everything that makes water unsafe. It won't eliminate heavy metals like lead or arsenic. It won't remove agricultural chemicals or industrial pollutants. It won't clear sediment, microplastics, or visible debris. If those elements are present in your water, this system alone is incomplete. This is where systems thinking becomes critical. Water treatment isn't a single step. It's a sequence of layers. A physical layer to remove particles, a chemical layer, if needed, to address dissolved contaminants, and a biological layer to control or eliminate living organisms. The copper-zinc system belongs to that final layer. Used correctly, it's powerful. Used in isolation, it can create a false sense of security. So the real question isn't whether this system works. It's whether you're applying it in the right place within the larger system. If this system works, if it's been studied for over a century, and if it costs almost nothing to implement, then a reasonable question follows. Why isn't it everywhere? To answer that, you have to step outside the science and look at the economics of systems, because technologies don't scale based only on effectiveness. They scale based on how well they fit into an economic model. A copper-zinc setup is simple. You buy it once. It lasts. It doesn't require replacement parts, subscriptions, or ongoing maintenance beyond basic cleaning. From a user perspective, that's ideal. From a business perspective, it's difficult to build around. Now compare that to modern filtration systems. They rely on cartridges that need to be replaced regularly. They depend on supply chains, distribution networks, and recurring purchases. They create a predictable revenue stream over time. That structure supports marketing, infrastructure, and widespread adoption. So what gets promoted isn't just what works, it's what fits the system. This doesn't mean there's a hidden agenda or a coordinated effort to suppress alternatives. It simply means that some solutions don't align with the incentives that drive large-scale systems. And when that happens, they tend to remain on the margins. Step back for a moment, and this stops being just a conversation about water. It becomes a conversation about systems and how we relate to them. Today, billions of people still don't have consistent access to safely managed drinking water. In many places, the infrastructure is fragile, expensive, or simply unavailable. When those systems fail, whether due to cost, disaster, or distance, the gap isn't theoretical, it's immediate. And that's where simple, decentralized solutions begin to matter. Not because they replace large systems entirely, but because they reduce dependence on them. What you've seen in this video is not a complete water treatment solution. It's one layer, a biological system that operates quietly, passively, and without external input. But the deeper insight is this: when you understand how systems work, you're no longer limited to the versions that are handed to you. You can combine layers, adapt methods, build redundancy into something as fundamental as water. Ancient civilizations didn't rely on centralized infrastructure because they couldn't. They worked with materials, time, and observation. Modern systems offer scale and convenience, but they also create dependency. And somewhere between those two approaches, there's a space where knowledge becomes resilience. Once you understand the system, you don't just use it. You think differently about everything built around it.